Hey class, today we're going to be doing section 2.7 from college algebra, which is all about inverse functions. So first we're going to talk about what an inverse function is. So graphically, and I know that this little box doesn't really talk about it, but graphically what an inverse function is a reflection of, say, a function f of x over the line y equals x, and that'll give you the inverse function. So all the points on the original function, if all of the points were x comma y, then the inverse would be all the points y comma x. So you would switch the x and the y values. I know that might be a little confusing. Let me do it this way. So a comma b, if that was a point on the original function, then the inverse would be b comma a. It would still have an x first and a y second, but we would be switching all those values. Another way you can determine whether two functions are inverses of each other algebraically is by taking the composition of the two functions and seeing if it simplifies out to just an x. If you're not sure how to do the composition of two functions or do composite functions, then you can watch my previous lesson. So let's look at an example here. I want to verify that these two functions, f of x and g of x, are inverses of each other algebraically. So what I want to check is to see if f of g of x equals x. And then I also want to check the other direction, that g of f of x equals x. So I'm going to do each one of these, f of g of x. So I'm going to take the f of x function and kind of picture x as a blank, and then I'm going to input the g of x function into that blank. So x minus 2 over 3. Now I just want to simplify this, and when you simplify very carefully. We need to follow order of operations, and in order to communicate that to your teacher or your grader, you want to just do this one step at a time and don't cancel out more than one thing at once. So first think, okay, what two things cancel out first? And there is a right and a wrong answer here. The 3's are going to cancel next. If you canceled the negative 2 and the positive 2, you'd actually be incorrect. So you have to be a little bit careful. This ends up being x minus 2 plus 2, which then equals x. So it works out, but you have to show me one step at a time so I know you're doing those in the right order. Now I want to check g of f of x. And so I'm going to use the g function, which is blank minus 2 over 3, and input the f function into that blank, so which is 3x plus 2. So similarly, we have to be careful, only one step at a time, which pieces cancel first. It has to be the 2 and the negative 2. So I end up with 3x over 3, which equals x. So yes, the two functions are inverses of each other. Now, if I have a function and I need to find the equation of the inverse, it's going to be a different process. So step one, what we're going to do first is we are going to switch the x and the y. So remember, f of x is just a fancy y. So I have y equals x cubed plus 1, and I'm going to write inverse, and then I'm going to switch the x and the y. So I end up with x equals y cubed plus 1. My second step, my goal is to get y by itself. So in order to do that, we want to kind of isolate y. So I'm going to be moving this 1 over here, x minus 1 equals y cubed, and then doing the cube root of both sides. So cubed root of x minus 1 equals the cubed root of y cubed. That gets rid of that cubed function. So I have y equals the cubed root of x minus 1. Now, one more step. You think you're done, but you're almost done. We need to write our formatting a little differently. F with a little negative 1. It looks like an exponent, but it's not. It's just notation. So f inverse of x is how we say that, equals the cubed root of x minus 1. Now, the domain and range of these two functions, it's, this is not the best example to talk about it. The domain and range of f of x being a cubic function, domain is going to be all real numbers, and so is range. And our f inverse of x, our cube root function, is going to have the same domain and range, but really with inverse functions, what's really cool about domain and range is that they switch. And I know that we don't see that here, but the domain of your original function becomes the range of your inverse, and the range of the original becomes the domain of the inverse. And unfortunately here they're all the same, but we're going to see an example at the end of today where they're not. So you can kind of see that relationship. All right, so let's see. Let's go down to the next example. So we want to find the inverse of this function. It's a little different, but same basic steps. So the first piece, I can rethink about this as y equals x plus 2 over x minus 3. And then for my inverse, and I always like to write the word inverse so that I'm communicating to my grader why I'm switching x and y, so what I'm doing here. I'm going to make it x equals y plus 2 over y minus 3. Now I need to isolate the y. We have two y's, so we have a little bit of work to do here. The first step, I want to get that denominator out of there. So I'm actually going to multiply both sides of my equation by y minus 3. And I'm trying to rewrite this here, color code it. So in doing that, I'm canceling out the denominator on that side of the equation and in a sense moving it to the other side. So now I have y minus 3 times x equals y plus 2. I can distribute this x in. I get xy minus 3x equals y plus 2. Now let's get our y's together on the same side of the equal sign. So I'm going to subtract y here. And I'm actually going to add 3x to my other side as well, just kind of trying to get the rest of the stuff over there. So xy minus y equals 3x plus 2. Now, when you have two y's like this, they're both on the same side of the equal sign. There's nothing else on that side of our equation that doesn't have a y. What we can do is we can factor the y out. So if I factor out the y, I'm left with x minus 1. And what that does is it allows us to take the two separate y's and kind of combine them into just one singular y. And then I can divide both sides of my equation by x minus 1 to get y by itself. So 3x plus 2 over x minus 1. I want to rewrite this. Our original function was f of x. So I'm going to have f inverse of x equals 3x plus 2 over x minus 1. Now we're almost done. In the last function, we had a cubic function and a cube root function for our inverse, and the domains weren't restricted. They were all real numbers. But anytime we have a function with a restricted domain, it's really nice to write what that restriction is to tell your grader that you're really thinking about what you're doing and what this function is. So if you notice, the original function had, and I'm going to highlight this, had an x can't equal 3. What that's there for is to show you that we have our function, but when x is 3, it makes that original f of x function, it makes the denominator 0, which makes it undefined. So it's not part of our domain. And so we're only taking the inverse of the part of the function that exists. So for all x's except for x equals 3 for the original function, but now in our inverse function, it's a little different. We don't need x not to equal 3 anymore. We need x not to equal 1 because now we have an x minus 1 in the denominator. So if x was 1, it would make that denominator 0. So let's graph each function really quick and then talk about domain and range so we can kind of see this relationship. So f of x, I'm going to write it over here, f of x equals x plus 2 over x minus 3. So it may have been a while since you've graphed something like this. So I'm just going to do it pretty quickly. If you're not following, it's okay. You can always plug this into Desmos and kind of see what it looks like for now. So I have a vertical asymptote at x equals 3, and I have a horizontal asymptote at y equals 1. And then let's see, if x was 0, I'd get a negative number. So my function is going to look something like, and I'm just going to do a really quick sketch here. It's going to look something like this and this for f of x. Now, I didn't go through exact points, but I have the right asymptotes and my graph is in the right spots. Now, if I graph the new function, I have a vertical asymptote when x equals 1 because x can't be 1. And I have a horizontal asymptote when y equals 3. So if you notice, those switched. My y equals 1 horizontal asymptote becomes x equals 1 vertical asymptote. And the vertical asymptote at x equals 3 became a horizontal at y equals 3. And then let's see, if I plug in a 0, I still get a negative number. So I'm going to have a graph something like this. All right, so another way to think about this, again, I mentioned it earlier, is if I take the original function and I take the line y equals x, which goes through the origin and exactly diagonal with a slope of 1, and I flipped our function over that line, I would get the inverse function f inverse of x. So now if we look at the domain and range of these two functions, so f of x versus f inverse of x, the domain of f of x was all real numbers except x couldn't equal 3. And the range was all real numbers except y couldn't equal 1. Now our inverse has a domain of all real numbers except x can't equal 1, and a range of all real numbers except y can't be 3. So we see that inverse relationship between our domain and range for our inverse functions. All right, let's talk about the horizontal line test. So we have a vertical line test, which we've used a lot. An equation y is a function if any vertical line intersects the graph exactly once, or no more than one time. The horizontal line test is a little bit new, but it's a really nice, easy way to tell if a function has an inverse that's also a function. So a function f has an inverse that is a function if any horizontal line intersects the graph of f. So we don't actually have to graph the inverse to see if the inverse is going to be a function. We can just look at the graph of f, and it's similar, but we're going to use a horizontal line and see if it intersects the graph of f exactly once. So let's look at this here. So these are all graphs of f of x. So these are not inverses. These are just f of x, and I know I'm using f of x a lot. It could be g of x. It could be h of x. So now, which of the following graphs represents functions? The graph represent functions that have inverse functions. So when they say inverse functions, now everything has an inverse. I can switch x and y and isolate y. I can take a graph and flip it over the line y equals x to any graph. I can find an inverse of any graph or any function. But will that inverse be a function? So this isn't asking which ones of these have inverses. This is asking, will the inverses be, or will the inverse be a function, is what it's asking. So it's a little tricky when you read that question. It's not as obvious as I wish it were. So the first one, f of x, I can use my horizontal line test. And if I draw a horizontal line anywhere on f of x, it's only going to intersect f of x once. So that means, yes, f inverse of x is a function. And then I am actually going to change some of these. I'm going to make this h of x, and I'm going to make this, I don't know, m of x. Why not? Okay, so now if I use a horizontal line test on h of x, it crosses my graph more than once. That's a problem. So even though we can find an inverse of h of x, it's not going to be a function. So no, h inverse of x is not a function. I don't have to graph the inverse to figure out that the inverse won't be a function. Similarly, with m of x, I have a bunch of intersections here with my horizontal line. And again, I could have put the horizontal line somewhere where it would only cross once, but we need to make sure every horizontal line possible would only cross once. And that's not the case. So no, m inverse of x is not a function. And then our last one here, g of x, it doesn't matter where I put this horizontal line, we're good to go. So yes, g inverse of x is a function. If you ever see the word invertible, again, it doesn't mean that we can find the inverse. It means that the inverse will be a function. So if f of x is invertible, it means that the inverse is a function. It would pass the vertical line test if I graph the inverse. So just in case you see the vocabulary pop up later. All right, so graphing inverse functions, the graph of f inverse of x is a reflection of the graph of f of x about the line or across the line y equals x. So I like to explain this to my students like it's a beautiful butterfly. And this is like the butterfly body here, body. And then if your wings spread out from there and they're perfectly symmetric, looks like a butterfly of some sort, then you have two inverse functions. If there's any asymmetry, anything that's not perfectly symmetric, then it's not an inverse. So let's look, oh, and the other thing, here's that A, B, and BA, so we can switch all those points there. Also good to look at that. So finding an inverse of a domain restricted function, we're going to do kind of everything together here. We're going to find the inverse. That means find the inverse equation. We have domain restrictions, and then we're going to graph it. We're going to look at the graphical properties of those two functions, and then talk about the domain of both. So all of it together in one example here. So the first thing I'm going to do is, again, I'm going to rewrite this as y equals x squared minus 1. And so for the inverse, even though it doesn't specifically say find the inverse equation, if it says find the inverse, I want you to find the equation. And I want to see all these steps. So I'm going to switch x and y and then get y by itself. So if I add 1 to both sides, I have x plus 1 equals y squared. And then if I square root both sides, and remember, if you're solving for a squared item, by taking the square root of that term, then we have two answers. So if x squared were 9, then x would be 3, but x could also be -3. We're always going to have two answers for that squared piece. So when we use that square root, we have to do plus or minus. So I have y equals plus or minus the square root of x plus 1. Now, the problem with this is I had a domain restriction of my original function. So if I were to graph f of x equals x squared minus 1, so it's like a parabola shifted down 1 unit, and I could graph the entire thing here, 1, 2, 1, 2, 3, 4, so 2, 4, because I'm squaring it. This would be the entire graph of, of f of x if it were not restricted. So we actually don't have this whole thing. I'm going to erase part of it in a second. If I graphed the entire thing of f inverse of x, if I graphed both the plus and the minus, so the positive square root of x plus 1 and the negative square root of x plus 1, I'd get this entire parabola reflected over. I'd have a positive square root and I'd have a negative square root. So it would look like that sideways parabola. But we have a domain restriction originally for our f of x function. I only want to keep the part of my graph where x is greater than or equal to 0. So I only want to keep this section of the graph. This is f of x with that domain restriction. Now they could have told us to keep the other half. So make sure to really think about which direction do they want you to keep. And then you have to decide whether or not you want to keep the plus or the minus. Which one are you going to keep based on the side of the graph that they want you to be focusing on? So in this case, all of those x values of my f of x function from where it starts and goes, those are all positive x values, which means if I switch that for my inverse, I want all positive y values. So I'm just going to keep the positive square root of x plus 1. This is a really tough concept to really understand. If they wanted us to keep x less than or equal to 0, the other half of my original parabola, I would have kept the negative in front of the square root of x plus 1 for my inverse. So really, really think about it each time. Don't just assume it's always the positive. So now if I'm going to graph that, I'm going to have, and I'm going to do it in a different color here. So square root of x plus 1 is going to be 1 to the left, and then 1, 1, square root of 1 is 1, square root of 1, 2, 3, 4 is 2. So it's going to look something like this, f inverse of x. And then if I really want to be sure that I have a beautiful butterfly, graph the line, just a dashed line of y equals x through your graph. So this is the line y equals x. Now, does it, if you look at that as like the butterfly body and you look at each side of that, are they perfectly symmetric, like beautiful butterfly wings? Yes, they are. So I know that my inverse is correct when I graphed it. Now, I don't have to write any domain restrictions. We will. Sometimes it's nice to do it. It didn't ask me to, but I will anyways. So for f of x versus f inverse of x, my domain of f of x, remember they restricted it. Usually the domain of a parabola is all real numbers, but they wanted us to focus on just x greater than or equal to 0. And then the range, if you look at that original f of x on our graph, it started at -1 and went to infinity. Now I'm kind of mixing interval notation and non-interval notation, so I'm going to go back and I'm going to write 0 to infinity so I can have, so this is the same as x greater than or equal to 0. This is the same as y greater than or equal to -1. I prefer interval notation. All right, so then f inverse of x, my domain is from -1 to infinity, or x is greater than or equal to -1. My range, if we look at that starting point for f inverse of x, the y value is 0. So my range is going to start at 0 and go up. So y is greater than or equal to 0. And look at that beautiful inverse relationship here. The domain becomes the range becomes the domain. And hopefully that's pretty much it. That's everything in one nice example. And that's it for today's lesson.